Inga ma'am, hello. No issue, no issue. You are like you are dealt in deep, right?
Hello. Dr. Sivaneasan, sir.
Hello.
Hello.
Yes, can you hear me?
Yes, sir. Good afternoon, sir.
Good afternoon.
Shall we start the session, sir?
Yeah, sure.
On behalf of SNS College of Engineering, Coimbatore, once again, a warm welcome to you all, dear participants, for the session 12 of the 6 days ATAL online FDP. Today, it's our honor and privilege to have Dr. Sivaneasan Balakrishnan, sir, Associate Professor of Singapore Institute of Technology, Singapore, with us today. He is an accomplished electrical engineer specializing in power engineering with a focus on microgrids, smart grid technologies, and renewable energy systems. He has received his Bachelor of Engineering and PhD degrees in Electrical and Electronics Engineering from Nanyang Technical University, Singapore in 2007 and 2012, respectively. He began his career at the School of Electrical and Electronics Engineering at Nanyang Technical University as a research engineer in 2011 and later as a research fellow until 2015. He transitioned to academia as a lecturer at Nanyang Polytechnic in 2015 before joining the Singapore Institute of Technology in 2019 as an assistant professor. Since 2023, he has served as an associate professor at Singapore Institute of Technology. He is also recognized as a specialist adult educator under the Institute of Adult Education and as a chartered engineer registered with the UK Engineering Council. His research focuses on applied projects that address critical challenges in the energy sector. His contributions include developing advanced metering infrastructure, condition monitoring systems, renewable energy technologies, energy storage systems, electric vehicles, building energy management systems, demand response, and smart grids. His notable projects include the partial discharge waveform identifier, which automates the detection of partial discharge with high accuracy and has been operational in a local power grid since 2021. Another significant achievement is the deployment of a shore power management system at Sembcorp Marine Toss Boulevard Shipyard in 2018, which improved sustainability and productivity by eliminating manual and paper-based operations. Dr. Sivaneasan has published over 30 technical papers and co-authored a book chapter on vehicle-to-grid systems in Energy Storage for Smart Grids, Planning and Operation for Renewable and Variable Energy Resources. His innovative works has received multiple awards, including the Best Innovation in Renewable Energy Award at the National Instruments ACAN Graphical System Design Achievement Award and the Best Paper Award at IEEE International Conference on Power Engineering Applications in the year 2022 for his industrial IoT-based electrical asset management system. Through collaborations with strategic industry partners, Dr. Sivaneasan integrates new technologies to enhance productivity and sustainability across industries. His dedication to innovation and applied research has solidified his reputation as a leader in power engineering and smart energy systems. So we are very happy to welcome you. Over to you, sir.
Okay, thank you so much. Thank you so much for the introduction. I hope you can hear me clear.
Yes, sir.
Okay, let me share my slides. Are you able to see my slides in full mode?
Yes, sir.
Okay, sure. So first of all, thank you to Dr. Jabarani for inviting me to share some of the works that I've done in the condition monitoring systems for smart grids. So today, my title is supposed to be partial discharge diagnostic, but then I thought I should also explain a little bit about maintenance and then how we do condition monitoring and also predictive analytics or predictive maintenance in a electrical system lah. So I'm a professor for the electrical power engineering program at SIT. So before I start, I probably think that I should introduce the university a little bit. You might not have known. So we are a University of Applied Learning. We are basically very industry focused degree program. So we don't offer now we don't offer electrical, electronic engineering, that kind of thing, but then it's more focused like electrical power engineering, manufacturing and mechanical engineering and so on. So it's more focused on the industry based on the demand of the industry in Singapore. And also what we do is we focus on growth industries, and that's the reason why we also do applied research. So I think you have seen Dr. Manoj's presentation earlier. There's so many work that is very important to be done in that areas. But what we do at SIT is we want to work very closely with the industry. So you will not see many of our papers being published because when we work with industry, there are a lot of IP issues and so on. So papers to be published are something very difficult. But then what we see is our projects are more closer to commercialization. So we have our IPs, licensed to the industry, products deployed in the industry, and so on. So that's how we differentiate ourselves from the other two universities, our big brothers here, NTU and also NUS. And so we complement each other. We work with them. So they do the blue sky research, the very more fundamental research, and then we do bring them. Then we bring it closer to the market commercialization. That's how we do research. So it's going to be a little bit more different than what you have heard from Dr. Manoj. But then the idea here is that both are important, and we need to then translate whatever we do in the traditional research to the applied research part lah. So SIT is the sixth university in Singapore. We only have 6 public universities, and we are the third largest now. And we have about 39 degree programs. We have 5 schools, engineering schools, in chemical engineering and food technology, IT, of course, and then some other schools. And we work with university partners from overseas. In particular, for electrical power engineering, we work with Newcastle University. We have TUM, DigiPen, and so on, University of Glasgow. So we offer dual degree programs with them, and they teach half of them. We teach half of the curriculum. So that's about SIT's. Sorry, I should actually change it to the current campus. So we moved in. It's a bit of old slide. We just moved in September. So it's a new campus. It's a campus that's we have moved from 5 different satellite campuses to one campus that we have built for the last 5 years. The advantage that we managed to build this in teaching in mind. So many of the things that is built as for service will be used for research as well as teaching. So this campus can accommodate 12,000 students. It is built to be co-located with the business district and also the residential unit. So we have the consumer, the industry, as well as the school in the same location. The reason being is that, for example, our students can go into the industry, they can work there, and then they can come back and then do small, short classes, and then they can go back to the industry and work there. So there is a symbiotic kind of relationship where the students can then gain industry knowledge at the same time while studying. And all the labs are basically equipped with industry relevant equipments and tools. At the same time, we have established 5 different living labs. One of them are the energy living lab. This is basically a microgrid. We have about 10,000 square meters of PV on the rooftops of the buildings in the campus. We have a district cooling system for the campus cooling, and we have more than 10,000 sensors deployed. Solar PV, we have about 1.8 megawatt peak. thermal, solar thermal. We have energy storage about 3 megawatt hour. Many chargers, about 80 plus chargers, EV chargers, and out of that we also have V2G. Dr. Manish also talk about V2G. We have 10 V2G chargers that we just going to install as part of a research grant. So all these are things that will help us to do more research, as well as help translate this to teaching. And that's, I think, what's important today. How do you then translate whatever we do in research into the teaching, so that the students stay relevant in whatever we are teaching them. Okay, so today I'm talking about maintenance of electrical systems. So basically, when you talk about electrical systems, we are talking about many equipments, right? There's so many equipments in an electrical system, from generation, transmission, and distribution system. All these require a very good maintenance strategies, and which is very is a very important thing, which may be overlooked due to the cost, right? So today I just want to share what are the things that is important and how we can then take care of them in order to ensure reliability in the power supply, which is very important. So when you talk about electrical system, very unlike mechanical installations, right? Electrical systems they actually produce very less noise, right? Or maybe no noise at all. And they tend, what happens is, because of that, we tend to overlook the importance of maintenance until a blackout or a hazardous emergency occurs. So and as you know, electrical equipment, as soon as you install them, they start to degrade as a process. It's a very normal process. But when you leave that unchecked, the degradation can cause a malfunction or even electrical failure. And this it becomes very critical, because electricity is very important, and it could be supplying to critical infrastructure like hospitals and so on. So, and even worse is that this degradation of the equipment can then be caused by other external factors as well. For example, hostile environment within for example, a substation, or maybe because you overload it, and then there's a severe duty cycle, too large on and off kind of operation. Even recently we had some discussion, some issues in the what do you call that, rail network, electrical rail network in Singapore, where the transformers are switch off during the night and then turn on in the day, which is not something that we should do, because the duty cycle creates a severe inrush current during the turn on periods, which we don't want to subject transformers to that. So this kind of activity will then also cause significant degradation in the actual operation or the behavior of that equipment. So in Singapore, we have this Singapore Standard 538, which is a code of practice that covers the maintenance of electrical equipment for voltages up to the 22 kilovolt. And the idea here is basically we want to enhance and ensure the safe operation of electrical installation, where the aim is basically to reduce the risk of breakdown, and also which will eventually cause an interruption of supply. And this electrical installation basically covers the fixed installation, not the temporary installation, like you have a fair or something, then you have a temporary electrical installation, not that one, but it only covers the fixed installation, and does not include all the appliances, the fittings, the lights, and so on. And I think we also have it in India. We have the Central Electricity Authority, right? They basically provide the regulation and guidelines for electrical installation, safety, as well as maintenance in the power generation, transmission, and distribution network. I think we also have at Singapore, we call it the Building and Construction Authority, which takes care of the built environment. So in India, probably you have the National Building Code in India, right? NBC, which covers the electrical installation within a building. So all these are basically the different regulations or policies that's in place for us to ensure that the maintenance of electrical assets which are critical are taken care of. In Singapore, the voltages are a little bit different. Our primary distribution voltage is at 22 kilovolt, and our secondary distribution is at 6.6 kilovolt, right? And then of course the consumer use is at single phase 400 volts. And when you talk about what do you call that, maintenance, right? A very critical aspect of when you do any operation or engineering is the maintenance strategy, right? How do you strategize the maintenance of any equipment that is or any system that is being operated? So this slide here basically illustrates three primary categories, right, of maintenance. We have what do you call that, the reactive, which is let me just give my pointer, right, which is the on the left hand side, and then we have the active as well as the proactive, right? So each of these approaches have very distinct characteristics and application, and we are not telling one is better than the other, but then in a system, we will talk about it in a short while, we need all three of them. So reactive maintenance offers often referred to as a run to failure kind of an approach, right? So you run it until you fail. Then it basically involves taking action only when a failure or a malfunction basically happens, right? So within this, we have two types. One is a deferred maintenance, right? This is when the failure is locked and then scheduled for later repair. So you don't immediately repair. And this typically happen when you have a non-critical equipment where the immediate action is not so important, or maybe you already have a redundant set. That means, for example, you have two back transformers, one backup by another, which can take up the entire load. Then this is basically not a very quick repair that you might need to do, because the second backup can take the entire load. The other one, of course, the immediate maintenance, which involves taking action immediately after the failure, and so that we can restore the functionality as quickly as possible. And this is actually very important when you have a critical system where the downtime that is impacted due to the loss of that equipment is very significant. And the reactive maintenance may seem to be cost effective initially because you don't have initial investment and so on, but over time the lack of this foresight, right, that can result in high cost, because you have unplanned downtime and potential of failure or damages to any other systems. So that is potentially the problem when you have what do you call the reactive kind of maintenance. On the other hand, the middle one is the active maintenance approach, which is basically a transition from a purely reactive kind of an approach to a very proactive. So it's in between both of them. And the later one is also called the preventive, right? So we have a corrective one, then we have a preventive one, then the last one is a predictive one. So the preventive one, basically the maintenance tasks are performed at a predetermined interval. So this is what we actually very commonly do in Singapore for mid-critical equipments. So you have a predetermined interval. Every 6 months, you have your maintenance team to go down to do measurement of critical parameters, and then use that critical parameters to then determine the condition of the equipment. Or it could be also based on the manufacturer's recommendation, or what do you call that? They are based on their operation experience. They might tell you, you should do 3 months rather than 6 months. So this is you can then determine what is the interval of these predetermined schedule routine checks. And the tasks which are typically scheduled or routine basically aim at preventing the failures before they occur. So you will then, based on that maintenance schedule, you will know that, because many of these equipments do not fail immediately, right? That means you have a problem and then immediately you fail. So it actually takes time to fail. There is a time interval for it to fail since the first show of problem, right? So we have time to then work on, but then there are some unfortunate incidents where immediately after you do one of your checks, the next couple of days or a few weeks later, before the 6-month lapse, you start to have significant what do you call that, damages. And then before the next interval, then the failure happens. That is also some unfortunate incidents like that. But preventive maintenance basically help to reduce the likelihood of an unexpected breakdown, right? So which may also result in inefficiencies because not all equipment may require servicing at fixed interval, right? But this is like not there nor here lah. So that we have something in place, but then it could be a bit more expensive, but then it is worth doing it as it helps you to detect problems earlier. And of course, the extreme light one is the most advanced strategy, which is a proactive maintenance. We also call it predictive maintenance. So this is basically aimed to anticipate and prevent the issues before they happen. And what they do is we use data and real-time insights, right? So this predictive maintenance have two approaches as well. One is we call it CBM, which is condition-based maintenance. This is basically relying on monitoring the actual condition of the equipment, basically to analyze, when the maintenance is required. So if you think that, there is a degradation happening, and then you can call for maintenance. So it's not fixed. It may happen very quickly within 2 months, 3 months, or you can prolong from 6 months to maybe 1 year, 1.5 years. And what are things that we do probably here are things like vibration analysis, thermography. If you're talking about substation panels, right? What do you call the high voltage panels? Then you probably do thermography, or if a transformer, you do dissolved gas analysis and so on. So all these information are then used to predict wear and tear. All right. The other one is what we call the data-driven maintenance. So this is basically leveraging on technologies such as IoT or machine learning or AI to analyze large set of data that you basically collect, and then you do trending, and you are able to then do pattern analysis to predict what is the potential failure. So these strategies are highly efficient, and it is aimed to minimize downtime, and then optimize the resources used. So you don't have to, immediately do maintenance. You do maintenance when it's required, but the challenge here is the investment, the initial capital investment in the technology as well as the training of the staff, right? In order to use these solutions, may be a little bit higher, but in the long run, it could be very useful. So each of these maintenance strategy has its place, right? Depending on the nature of the system or even the organizational priorities. They know, the organizational priorities can be, focused on, for example, anything that relates to the data server and so on, but the highest priority. So the maintenance of this cannot be, very corrective or preventive. It should be predictive. Based on that operational priorities, we also can then determine what is the maintenance strategy. Reactive maintenance, for example, right, is appropriate for very low risk, low cost systems, right? Which, failure, you can, easily replace it, and then you can then quickly put in place again. Preventive is a bit between the two, but then it is actually a balance of cost as well as reliability. So it's, you're balancing cost and reliability. And of course, proactive is very, very much about critical systems where the downtime is very costly. And, you also must have the advanced technology that is available. And what is critical here is to understand these strategies, and you enable organization to optimize their operation, and so that they can improve reliability and manage their cost effectively. Why is it important for me, this for my team, is because when we work with the industry, we don't want to then go and propose to them a solution that is high cost for a low risk system, right? Eventually, they will then find it not useful at all, right? And it is high cost, and it may not be useful for them. All right, so we want to then understand which are the high criticality equipment or system in their network, and then propose the appropriate strategy. And that's where industries find relevance in what we do, and how it then impacts their efficiency, their productivity, their operation. Okay, so as we know, the switch gear is, for example, right, or control gear, they are typically examined for for a period of time, right? For example, when you have a switchgear installed, right, you always have a first year maintenance, and then you have a routine maintenance to see what happens, over 6 months or over 12 months of the use of the equipment, right? And then we also quite quickly when there is a, because there is always a what do you call that, burnout period where when you install that one equipment, right, the first 12 months is actually critical. We cannot expect, in fact, in Singapore, there are many incidents where equipment, like especially in transformers, right, they fail immediately within a few months after installation, right? So it could be design problem, it could be, uh, some other issues, but then this first 12 months, right, of commissioning is very, very important. So it is always advisable to inspect all the equipment shortly before the expiry of the manufacturer warranty. So typically you get 1 year, 2 year manufacturer warranty. So they are typically operating that period. And this burn-in period will be very important to then understand how the system or the equipment will operate in the subsequent years. And then we know what is the equipment's vulnerability based on this initial problem that we can then diagnose in the first year. So the interval between the maintenance and operation may be based on the number of, what do you call that, operations that's performed by the switchgear or the control gear. And this can be recommended by the manufacturer, or it could be just, fixed time intervals, for example, every 6 months and so on. So this chart, if you see, is actually available in that SS538 that I showed earlier. So we determine the frequency based on this table, right? If you don't have a standard manufacturer suggested interval, then it is based on this, what do you call that, chart here. So if the equipment criticality is very low, and then the equipment condition is good, in fact, you can then operate it in, do the maintenance interval every 2.5 years, which is quite long, right? So that means the environment is good, the load factor of that means the utilization of the equipment is less than 50%, and the age of the equipment is less than 5 years. This is how we categorize good, right? So then it can be actually monitored every 2.5 years. And then the other one is the lower side, which is poor. That means the environment is poor. Poor environment meaning maybe the substation is not properly ventilated. It has a very high temperature surrounding ambient temperature. So these are basically, what do you call that? Not a good environment. So, or to say a good environment, basically you have a very clean area, dust free, very well ventilated, and that is basically a good environment. So the load factor is basically how much you use, right? The duty cycle and so on. So this is basically greater than 70. That means that you are loading for example, if a transformer, you're loading the transformer 70%, greater than 70%, right? So, and then the age of the equipment is greater than 12 years. So this is basically where we then say that this is at the poor end of the equipment condition. And the minimum requirement for a low risk equipment is 1 year. So every 1 year, you're supposed to then do what do you call that, a maintenance. But if the equipment criticality, example, medium criticality. So low criticality, especially residential buildings, these are low criticality, religious buildings, places of storage, for example, godowns and warehouse and all these. So these are basically low criticality category, what do you call that, systems. And then medium criticality are like, small, medium enterprise factories that do not operate on a 24-hour basis, office buildings, schools, public places, and so on. These are medium criticality. Then, of course, high criticality are where you do medical treatment, healthcare in person, hospitals, polyclinics, or factories, hotels, and all these that operate on a 24-hour basis. These are all high criticality category, and this is based on Singapore. So then the based on the criticality of the system, that you're monitoring, the timeline actually changes. The more critical it is, the quicker that you must do maintenance every check every year. The interval is now 6 months once. And of course, the average one is all between the two, is between the good to poor, load factor between 50 to 70%, and is 5 to 10, 12 years kind of average equipment. So then based on this, right, this is the recommended practice. In Singapore, when you have equipment, you then follow these conditions and then you can determine what is the required. So you should go beyond. That means I'm recommending 2.5, you go 3, and something happens in between 2.5 to 3, then we are subjected to scrutiny here, right? So we are typically then making sure that we do assessment, less than 2.5 years. So if it's a 2-year, typically the company will decide to do 2 years and so on. So this is how we then, decide what is the period of assessment that we should do. And lastly, of course, the post-fault maintenance. These are typically happen that, when you have a fault and then you then solve the problem, you repair, and then you do a post-fault maintenance, because you cannot then wait another 6 months after that the repair to do another. It could be shorter based on the recommended by the OEM, and it can be done in a few intervals, maybe 1 month for the next 3 months and so on. And this will then help us to ensure that the repairs work are then properly done as well. Okay, so these are typically the ideas of maintenance. Okay, so coming to predictive maintenance, right, and what you call the condition means maintenance. So these two maintenance strategies are very important when you do proactive maintenance. So basically, my work I do at SIT now is very much focused on either condition-based maintenance or data-driven predictive maintenance. So these are not same. They are typically they are confused to be the same, but actually they serve very distinct purposes, and they leverage different approaches to achieve the idea here is operational efficiency. So when you talk about condition-based maintenance, we are basically focused on monitoring the health of the equipment in real time, right? So for example, if I were to give you a use case, condition-based maintenance, you are using sensors and measurement tools to monitor the current condition of the asset. And then this basically allows you for timely intervention of based on the actual state of the equipment. For example, if you have a machine, right, and then you use vibration levels to basically determine the imbalance or misalignment in a machine, right? So this is typically for rotating machine. You do these vibration levels, then give you an understanding of the condition of the machine. For example, how its alignment is and so on. And we basically rely on real-time periodic measurement and of the parameters, right? So the parameters are measured in real time, or it could be measured every half an hour or 1 hour and so on. And typically in an electrical system, we measure things like temperature, we measure things like a partial discharge, pressure, or vibration data, and so on. And what we do with this data, the data basically you collect, and then basically the data helps you to identify if the asset condition deviates from this normal operation. So you will always have some kind of a threshold. So this threshold is what we use to then trigger the maintenance. For example, when your vibration is high, right? Then reading may indicate the need for immediate inspection. So then you trigger your maintenance team to go and check. So the data will then be used to against a threshold to compare and then tell that there is a need to go and check the equipment. So CBM is basically reactive in response to specific conditions. So it doesn't do anything, but then it actually avoids a complete failure, because once you exceed the threshold, it will then trigger for maintenance. So immediately you are able to then trigger or attend to a potential fault that can happen in a very short period of time. So the idea here is that it basically helps to reduce unnecessary maintenance. So if everything's okay, then it doesn't require for maintenance to be triggered. So it can happen within greater than 1 year, 2 year, or 2.5 year. And it also helps to optimize the resources and also obviously reduce the cost because once you have no maintenance still need to be scheduled, because scheduling maintenance is not easy. You need to inform your customers that you're going to do shutdown. You need to trigger, you need to bring in licensed electrical engineers to come and do shutdown. It costs a lot of money. So, and also, you are going for a shutdown means your business are affected as well. So it's basically a time-based kind of a preventive approach. And data-driven maintenance basically looks at more advanced approach which uses predictive technology. So there's the reason why machine learning and all this comes in. So uh, what we do is we of course integrate historical and real-time data, and then we use that to predict the failure and the performance degradation of a particular system. And this approach basically combines sensor data. You also combine, if you use only sensor data, then you basically do condition monitoring, condition-based monitoring, right? So, but then this approach basically will use multiple data sources, right? One is the sensor data. Probably there's a maintenance log. You probably have other external factors that are coming in to help you identify patterns and trends. Then it becomes data-driven kind of a predictive maintenance. And of course, there is always an advanced algorithm that analyzes this data to provide, insights in real time, and also suggests, preemptive actions for you to do. For example, AI can predict the wear and tear in turbine blades, for example, even before they are going to fail. And that will basically help us to do maintenance way ahead from when the problem will occur. And so the maintenance action compared to condition-based is very much about sensors, but this is a bit more about prediction rather than just a fixed threshold. If you exceed this threshold, you do maintenance. This is a bit more on a predictive. So I predict, what is the potential for failure, right? Sometimes you use remaining useful life and so on, right? So then we are able to then know, there is a potential anomaly happening. So how do I then trigger maintenance to happen? And of course, the advantage here is that you minimize all the unplanned downtime, and it's also help to reduce the maintenance cost. But of course, this is could be costly because it runs real time, does a data analysis, a lot of storage of data is important. But then that's why I mentioned it is important to decide when and where you want to do this. So when you look at performance to time of failure, right? So this is basically telling us that, predictive analytics can actually provide an early warning. If you see this point P here, this is the potential failure point. This is where the potential issues first become detectable, right? And it might be a slight increase in vibration, for example, or a small drop in the performance efficiency. And this subtle anomaly that is picked up by the sensor is very important. And the system is still functional, everything's okay, but this is basically an early warning that something is not quite right. Right. So and point F is the other end, extreme, where the point is the asset is no longer performing as it's supposed to be. And for example, the the pump basically stops to pump, or the motor doesn't operate anymore, or there's a catastrophic kind of a failure. So if you reach this point, then the failure has basically happened, and then this will then eventually lead to unplanned downtime, and will be very, very high cost when you want to deal with this. So the idea here is that we want to bring in predictive maintenance even before. So this is where you do preventive maintenance, which is good. We are able to then achieve something useful. But then we want to do even earlier, even when you start to see early warnings, and then you can do cheaper corrective actions, right? Maybe you will just tightening of a bolt, right? Rather than replacing an entire bus bar, for example. So the cost of repair or solving this problem could be much cheaper when you do predictive maintenance compared to preventive or corrective maintenance. So the idea is basically acting at or as soon as after point B will be very, very much more cost effective than waiting until point F. So because repairs are always repairs are always cheaper, and there is low risk of damages to other systems as well, right? And you can plan your downtime, for example, where example, I work with the airport now, so we can plan the downtime to be immediately after the holiday periods, so that no the not all the activities at the airport are affected, because holiday period, everything is happening in full fledged, so we can then plan the downtime accordingly, and that will minimize disruption to the business. So the idea here is basically we want to do it earlier, and it is much cheaper, although the cost could be higher. So why are we looking at this? Because uh, compared to predictive maintenance, or corrective maintenance can actually cost 10 times more. Although the capital cost of predictive maintenance is a bit more higher, the loss in the time, unplanned downtime, the potential hazard, because if it's a spark or it's a totally a blow of a transformer, the hazard is quite significant, and you actually need an extensive effort to then restore the operation. So this is very, very costly compared to this when you talk about the overall cost. And so what we do is we don't do everything uh, at a data-driven level or predictive level. So there are 40% of your asset which are basic assets that you don't have to do very costly condition-based monitoring or data-driven predictive analysis. It's only the 25% of your essential asset that you want to try to do condition-based monitoring. So these 25% of essential assets are basically, assets that are important. They are important, but their failure can be managed, right? So this is where we can then optimize the cost and the reliability, where you can actually prevent unnecessary maintenance but ensure continuous monitoring. For example, in an electrical system, in a substation, for example, the basic equipment could be very small auxiliary equipment like the heater in a enclosure, in a panel, right? The heater, it's a very small, what do you call that, failure or low risk equipment. All right, and then the important one maybe is the battery backup system for the control panel, right? And then the essential could be the medium voltage transformers. And then the highest critical one within the substation could be a high voltage circuit breaker, right? So these are the different equipments that can happen, and only 5% or 25% of essential can be focused on CBM and data-driven model. So we are looking at which one is the most critical, because their implication can cause you safety, operational, and financial implications. So we focus on that, and then we propose the correct solutions for the industry. I'll pause here for a while. Is there any question before I go on to the projects that I'm doing? Okay. So move on. So what we have done is we have worked on a few projects together with the industry. And if you look at electrical systems, right, we do maintenance in 5 or 6 steps. Inspection, operational checks, we do diagnostic of the test, and then we do servicing, we do examination. Examination is like, inspection. With, for example, addition of a partial dismantling that you have to do, and then you then supplement it with some kind of measurement or non-destructive test. And also you can do overhaul. Overhaul is is a replace or repair of a part after you examine it. And what we want to do in maintenance of electrical asset is not the last 3, but then the first 3. How do you then automate this process of inspection, operational check, and diagnostic tech? If you replace this is the manual interval-based approach, interval-based work that a maintenance team need to do. If you can automate this by condition-based monitoring or predictive maintenance, and then that will save a lot of costs. If you look at the entire maintenance process, these are the top 3 that actually cost you a lot of money. For example, if you're talking about partial discharge, which we'll talk about shortly, currently what they do, for example, there are multiple ways to do partial discharge measurement. So ultrasonic is one of them, transient earth voltage is another. There is a need for manual offline measurement, right? That means they need to go down to the substation, every single substation, and then go down and do a measurement, collect the data, go back to the office, download the data, they look at the data, and then they analyze it. So it's a lot of work. And you need to do, for example, a small country like Singapore, we have 13,022 kV substation, 13,000. So this is a very, very small country. We are smaller than, I think, Coimbatore, I'm not sure. But then I think, we are very small. Of course, we are way smaller than the whole of Chennai. But then if you can move that into an online measurement system, install the sensor collects the data, measures it, do the real-time analysis as it goes. Whenever it goes above a threshold, then it triggers an alarm, maintenance stuff comes down, right? So, sometimes, very good systems, most of the systems are good when you buy from a good OEM. They can last years before it actually causes gives you some early warning. So you can save a lot of money by installing this kind of measurement system. Okay, of course, where are these assets? In a traditional system, of course, we have a generation system, transmission and distribution. This is our traditional power system, which is taken care by the utility company, right? And then we have the consumer, which is the customer side, which we don't care actually, right? So no, utility doesn't worry about the assets in the consumer side. They only worry the assets at the generation, transmission, distribution network. But moving into a smart grid, this is changing. There are a lot of other things that's coming into play. For example, at the residential side, there could be at the low voltage energy storage systems, right? There are smart meters that are being monitored. There is home displays. There is also control of equipment or loads in the home. At the generation side, you also now have not only generation stations, you can have cross-border interconnection. For example, in Singapore, we are buying electricity. We started buying electricity from Vietnam, Cambodia, hydropower plants that are installed in Vietnam and Cambodia, and then they transfer power through electricity networks across Singapore, Malaysia, and so on. So there are different renewable energy or grid energy that's coming from different networks. There are in the commercial side, you have electric vehicle charging station now. So there are many more other things that you are now required to monitor that can cause a disruption, not to the entire grid when they disoperate properly, right? So when they, for example, you're highly dependent on energy storage goes off, you lose one local generation, right? So then you need to start to ramp up this generation and so on. So whether are you able to sustain or not? So the reliability is impacted by many of the components across the network, no more on just the utility side. So it becomes a bit more critical. So there are many of these critical assets that need to be monitored. What we're focusing on is myself, right, in these projects that we are doing now. We are very much focused on the switchgear, transformers, cables and bus bars, as well as the renewable energy sources. In Singapore, unfortunately, wind is not an option for us. Our wind speed is very low at 1.2, 1.3 meter per second, which is way below the cutoff of commercial wind turbines, even on offshore sites. So wind turbine is not a go for us. So only option for us is solar PV now. And of course, we have energy storage. So these are the two distributed energy sources that I work with. And then, of course, all the grid infrastructure like the switchgear, transformers, and cables. So what we do is we adopt the ISO 13374 when we develop condition-based solutions for our industry partners. So 13374 is basically standards that's used for condition monitoring and diagnostic of machines, right? So these machines are defined as anything from electrical to mechanical. It provides a 7-layer kind of a framework for for data processing, for data analysis, for decision support, for information, how you present the information and so on. So it basically outlines how you systematically monitor the condition of any equipment, how you detect any anomaly or failure, and then analyze the data to understand what is the root cause of the failure. And then you make informed decision on when you do maintenance or when you do repairs. So these are the 7 what do you call that, layers are sensors, the data acquisition, data manipulation, state estimation, and then you have HA, which is the health assessment, prognostic assessment, PA, and AG is advisory generation, which is decides what is the decision that you need to take. So what I do is I basically work with the industry. We work on either develop the end-to-end solution from the sensor all the way to the analysis, or we adopt sensors, right? We adopt sensors from partners. For example, EATech, I work closely with EATech, a UK company, or on partial discharge measurement as well as low voltage condition monitoring. So they have their sensors. I don't have to rebuild my work. What I do is I use their sensors to get data, and then I use solutions. I develop algorithms to then help the companies that I work with to visualize this, right? For example, for this LV monitoring, low voltage monitoring system for their low voltage distribution network, I work with Changi Airport now, so for them to help to visualize, and also analyze the condition of the low voltage network. For PD, we work with Singapore Power. That's what I'm going to share a little while. And this is an offline system. We collect the data and then we go back and help them to easily analyze the data. And then, of course, end-to-end, we work with a company called Sunship, now EDPR. How do you establish the sensors for condition monitoring of solar PV systems? And then develop the data acquisition system and then do the analysis part. So this is the end-to-end. So you need to have that solutions also, as well as we work with partners to then use their sensors to develop solutions. Okay, so this is the project on partial discharge waveform identifier. So as I mentioned earlier, right, what happens is that every 6 months, over 13,022 kV substation, I'm not going up to the 66 kV, 230 and 400 kV. There are these are more what do you call that, numbers of substation to monitor, but at least at the 22 kV, we have 13,000 of them. And then, what they does is basically periodically go and then do the check, come back to the office, and it's a manual and individual inspection of the waveforms of the PD. And this is time consuming, and also it highly dependent on the capability of the what do you call that, officer that is monitoring. And imagine looking at so many data every day, you might miss, might have an error in your decision, right? So after they decide, they say, hey, there's a problem, then they alert the maintenance team to then do a further assessment. So this is time consuming, it's also costly, and it is also prone to man-made error. So what we did is we proposed a data analysis platform, or you can call it a software, that is developed to allow the frontline officers who actually do this measurement to efficiently analyze the site's TEV data using the tools that is used with our partner, which is EATech, and then analyze quickly and accurately the potential of PD, right? So the idea here is basically you allow the frontline officers to then extract this data from their devices, upload it into the platform. The what do you call that? The analysis will be done automatically to flag out if there is any suspected partial discharge occurrence in the data, and then inform the officer what is the percentage of likelihood there is a partial discharge. And partial discharge, probably I'll explain shortly. Right. So what we do is that the developed software basically does a what do you call that, identification of the waveform, right? So it basically consists of 3 components. One is the machine learning model, and then the interface between the machine learning model and the UI, And then of course the UI, because you are actually the officers are basically interacting to the UI. For them, all these are black box. So the machine learning model is built on Python. The front end is also built in Python, and then we are basically actually doing the actual processing and analysis of the waveform and using the model at the interface here. So the interface basically is also a Python script that loads the trained machine learning model. We use data that was good and bad data from the previous historical sightings of partial discharge, and then we train the model. And then he will then use the new data that is uploaded by the user and then perform an inference on the condition. So the interface also, actually we include a unzipping feature to automatically unzip the data from the device, because the device gives us a zip file of the many information that it collects during the measurement period. So we don't want the officer to go and unzip everyone and give us just the PRPD plot, for example. So we use all the data that is, we unzip it ourselves, and then we are able to make this very simple for them. And then the UI is of course also Python is a very user-friendly UI, and then you just need to upload and then run it, and then it will tell you what is the result. So as I mentioned earlier, right, there are three types of PD. So partial discharge, there is surface discharge, there is internal discharge, and then corona discharge. So these are typically due to voids in a bus bar, for example. So surface discharge, if you look at the discharge itself, right, this is a typical PRPD plot. If you have a surface discharge, you can see a pattern that appears both in the positive and the negative cycle, or just the positive cycle, two positive cycles, 180 degrees apart. Right, so you will see there's two similar patterns happening. And for internal discharge, you will see a more one-sided pulse, which is asymmetric. And then third one is actually called the corona discharge, which is typically due to the localized discharge near conductors or sharp edges. When you're pointing edges, then this corona discharge can happen. And this basically appears as very sharp pulses in both half cycles. So, but the only issue here is these are operational data. So when we work with industry, you face with practical challenges. So these are operational data, meaning they come from the operational environment at the substation. So a substation is not noisy, but then there is a strong presence of random white noise, the buzzing white noise that you hear. And that is very evident in this diagram here. For example, this white color, dark, deep white are all noise, right? All are white noise. So what we did is we actually had to propose a new method. It was published in this paper here. And this method basically determines the baseline where this noise occurs for every individual plot, and then we subsequently remove it. So basically the idea here is that if there is a PD that is present, we don't do it for everything. If there is a potential for a PD pattern, then we will do the white noise removal by hovering these data points over the white noise. So the idea is if you have two clusters of points available, and then you determine the white line baseline, and then anything below that we will remove it. So we use a method called bucketing, 360 degrees of the sine wave, for example, and then we break it down to 36 buckets. So every 10 degrees is one bucket, and then we put in a very simple K means clustering to carry out with the two numbers of clusters or sets that we have. And then with this, we then can determine the bucket's baseline. And from there, any value that falls below this bucket, right, then we can then remove them as a noise. So we are basically taking out these data points into the basket, and then anything below these data points are then removed. So we publish this in Energies, and you can always take a look if you are interested. Okay, and in terms of how do you then determine the pattern, right? So we these are examples. These are the one that is before extraction, and this is after extraction when you remove the noise. And the extracted clusters are basically indicative of whether there is partial discharge or not. So all these are examples of partial discharge. You'll see it happening 180 and the clusters are happening there. So these are very sure partial discharge occurrence. So, but then we need features, right? So we have 4 different features that we have decided to use. So we, of course, use the length of the cluster. So every cluster will have its length, height, and then the gradient from top right to bottom left, and then from top left to bottom right. So these are the 4 features. So from these 4 features, we can then determine, whether the occurrence of a PD is there and how severe it is, right? So the severity is based on the amplitude of the points that we see there. So what we had was we had 450 plus PR, this called phase resolved partial discharge plots. These are 2D plots. We obtained it from our partner Singapore Power, which is our utility company. And out of these 340 plus were negative PRPD plots. That means there's no PD. And then 110 of them were positive PD, right? Which means the PDs are like this now. And these operational data will typically have different forms of PD. And then there is also potential. I explained 3 of the 3 surface, internal, and corona. There are some of them that has overlapping PD. There could be corona and surface happening at the same time, for example. And there is also a lot of white noise presence in a lot of these data. So it was a very operational data, which was very difficult to work on. Unlike, when you produce this in a laboratory, it is totally a different ballgame. So we did a simple ablation study on the features, see which one is actually more important than the other. Of course, I think all 4 were more important. So we used all 4 for when we deliver our solution. And what happens is that if you can see the first balance score here, so the what do you call that, the accuracy score, basically you are able to get a very high accuracy with very low what do you call that, false negative, right? Because when you talk about a business objective, the idea here is to have, if possible, 0 false negative. Because false negative meaning it is a PD, but then detected as a no PD, which is very dangerous, because when there's a PD, it could quickly develop to a catastrophic event, right? So if you have false positive, it's okay, because that means we just waste our time spending a maintenance team to do maintenance, right? This is a smaller problem than having a PD but then detected it as no PD. So this decision tree as well as random forest solutions actually gave us 0 false negative, which was very important. And then we do ablation study as well. And what do you call that? So this is the UI. I think this is a second version. We have even a later version now. Typically, the idea here is that they will upload the zip file, and then we automatically unzip it, and then we download all the files from it. There are many files within a zip file. You need to analyze all data. One of them is PRPD plot. So we also look at a few things. We look at number of pulse per peak, number of times they exceed the threshold. How we get the threshold is we determine by the mean and the standard deviation. And we also look at the pulse width. How, every pulse, how much is the width? So if the width is greater than 2 microseconds, then it's something more severe, that kind of thing. And after we analyze it, we then give them a decision, right? So for example, we tell them, based on all these pulse per peak, amplitude, and pulse width, we discuss this how the industry partner wanted us to deliver this. So it will tell us, based on a certain percentage, right? So what is the likelihood of the presence of PD? For example, the PRPD indicates yes, there's a PD, the pulse also indicates a yes, then it's 100% a PD. So if the pulse indicates a no, that means the pulse is not so significant. But then the PRPD indicates yes, then we still go for 50%. Anything greater than 50, they will then trigger what do you call that? Maintenance operation. Right? If there is no PRPD, but then the pulse is high, then it is a 20% is keep in view. That means you will keep them viewed, and then the next round you will check again. And then lastly is, of course, no PRPD, no pulse, and then it's 0%. So this of course, with agreement based on the what do you call that, operational requirement of the company. And then we develop this, and then currently it is being used in Singapore Power. Save them a lot of time, and it has over the last 1.5 years, right? This was reported in the beginning of this year, 95% accuracy with 0 false negative. So this is one of the work that we have done on partial discharge waveform identifier. You can take a look at the paper in Energies when you are free. So of course, there is also other project that we do in condition monitoring. This with solar PV system. Sunseap now is called the EDPR. It's a Portuguese company now. So we developed the entire sensor solutions and data acquisition system, and then we use that to then determine what is the condition of the asset, solar PV assets over a period of time. And you know that the assets can have two different problems. One is over time the condition of the asset will reduce, will degrade, and that will cause a reduction in performance, right? So as we reduce, we can then ensure the maintenance is happening. At the same time, there's also another problem is shading, right? So there could be partial shadings and so on. So are we able to then pick this up and then inform the maintenance team that there's, suddenly there's some shading happening and so on? It could be due to, bird poop or something, right? It could be so many reasons, not necessarily a tree. It could be any other reason. So these are the one that we are trying to highlight on top of, hotspots in the module, shadowing, probably shattering of the panels and so on, as well as inverter efficiency. So this is one example that we did. The blue one shows 2022 data, and then the what do you call that, yellowish or orangey line shows 2020 data. So we can see that things get degraded within a very short period. 2 years, we can see slight degradation in the output of the solar PV system, right? And then this is what we are trying to do, trending, and how we can then use this to understand end of life or remaining useful life prediction. This is the one that we did for shading. All right, so based on the shading, then based on the data that we collect from the sensors, we are then able to tell, there is shading happening, there is unshaded panels, from the comparison of the shaded panels, unshaded panels, then we can know whether it's panel shading or low cast of, maybe there is a cloud cover and so on. So that will basically help us to then quickly determine what need to be done next. So these are typically alarms that we send to the maintenance team to then for their review. They can then decide not to do anything, or they can decide to do something. And lastly, which is more recent now, we are working on a energy storage project. So this is together with the one that is installed in the campus. There is two problems when you have your energy storage declining in condition. One is, obviously there's a potential for supply disruption, but there is also another problem which is more severe, which is fire exit. Right? There are many types of batteries, electrochemical, thermal, chemical, electromagnetic, magnetic, as well as mechanical. But then there are many of the problems, especially thermal runaway being the greatest one. The internal heat that's generated within the what do you call the cells that cause internal temperature build-up. So this is the one of the biggest risks that we will see in energy storage. So these are many things that we want to study. What we did recently was study based on the data sets that we have from NASA. We actually have a battery storage cycler in the lab. So we have another set of data we just recently completed the data collection where, we have all the cycle data, and then we are going to do a similar thing that we have done for this. So battery basically degrades over time, right? And typically the reason is because of the charge discharge cycle, temperature of the ambient as well, the chemical reactions that happen within them, and so on. So the remaining useful life, which is basically the number of cycles before the battery reaches its end of life, if we can predict this RUL, it can basically help us understand when the performance of the battery will fall below a certain critical threshold. And this will help us to optimize the schedules and improve the energy management of the energy storage device. So what we did is we actually proposed an innovative method for optimizing the LSTM hyperparameters using a genetic algorithm. And of course, traditional approaches basically rely heavily on trial and error for hyperparameter determination, but especially you will face challenges in selecting an optimal parameter due to the very extensive search space. There is every battery behave differently. Same composition or same chemistry battery will behave differently. So what we have done is we propose a systematic methodology which not only identifies the architecture, the best architecture, but also introduce a very novel character or criteria for evaluating ANN performance and their complexity. So this optimized so-called genetic algorithm LSTM model is basically trained with curated NASA data. I think it's all available, and its accuracy we basically evaluate, and we evaluate or tune it according to the batch size, the unit size, activation functions, loss functions, and so on. So the diagram here basically shows the 70% training data set. So we use 70% data to train, and then we predict the last 30%. And we also done that for 30% training, 50% training, and so on. And what we basically are able to see is that this NASA data is basically, there are many data sets. So every data set is different. So it's a bit ambiguous whether which set of data you use. So we have used the B5, B6, and B18 because they are a bit more fuller in the data that is available. And these are just typical 18650 batteries with a 2 ampere hour rated capacity. So what we saw is that if you can see here, we have other types of simple LSTM, simple RNN from other literature, RVM, which is what do you call that, relevance vector matrix, right? Relevance vector machines. Then PLSTM is one of the best now in the literature, which is called parallel attention LSTM, and then we propose the GA-LSTM. So based on the 70% data, right, we can see that our system performs better than this PA-LSTM. With this is about 12%, 36%, and about 76% better than the PA-LSTM. But you can't say the same for the other two because there is a slight decrease in the accuracy. So if you have 70% of data, yeah, our solution is better, but then not necessarily for what do you call that, 30 and 50, we are not performing as well. So there's some further studies are being done now to actually close this gap. So a lot of work to be done. There's a lot of condition monitoring or predictive analytics work to be done in the smart grid environment. I think use of machine learning, use of new technologies in condition monitoring, and all these are very important. So quick conclusion. So maintenance of electrical asset must move towards the predictive maintenance approach, particularly for highly critical equipments. And it is important that we focus on two things. We must automate the monitoring. We also must automate the analysis. But there's a balance between the cost and reliability. So we cannot do it for everything. This is what we understand, because when we go to the industry, they, we can say all the good things, but then cost matters most for them. So we need to balance them out and find what is the most critical equipment that we need to monitor and then propose solutions for them. So that gives us an edge in terms of getting our product being deployed or commercialized by our partners. And data analytics is key, whether it's descriptive, diagnostic, or predictive, they bring advantage to the whole process. So as part of the faculty development program, I think they are looking at, what are the emerging technologies that's important for electrical engineering. And I think, how do you then bring machine learning techniques and artificial intelligence to then improve the condition monitoring and predictive maintenance of a power system is actually very critical, as we are forming the backbone of any infrastructure or any system in the industry as well as in the what do you call that, commercial world. Okay, any question?
While you're carrying out these works, did the data size have any impact on the results?
Yeah, obviously, the one that we had with the Singapore Power, right? We had over 450 plus data sets. It's not easy to get positive PD data sets, right? Because that means there is failure happening in your system. But because they had a very long history of keeping their data records, so these 110 plus PD positive data is a collection of 13 years of data, right? So by our partner. So if we don't have this, I don't think the accuracy will be so good, because we have all the PD, and then the PD had different PDs as well, because the 3 PDs must be there in order for us to do a proper accurate analysis or the model to be accurate. So having very good data, especially positive positive data, is critical. But then it really depends on our partners that we work with. And these are real data, right? These are operational data. So yes, the answer is obviously yes, but then we don't always have the luxury of doing it. But so work with whatever we have. That's why we think working with partners is very important. So the battery data that we are now working with NASA one, I have a partner who are helping me to do give me a set of data from their energy storage that's 2 years old now. So they have been collecting data from 2 years. So these are data that I will be able to pick up from the industry and then use it for my analysis.
Sir, is there any technique meant for small data sets? Any ML techniques meant for small data sets?
When you have a small data sets, I think very key is you can actually do transfer learning. So there must be, if you can, combine physics-based models with data-driven model, right? Then you can actually you can have smaller data sets. That is potentially one solution that can help us solve this problem of data set.
Thank you so much, sir. Thank you
Sure.
so much for.
Any other questions?
Dear participants, do anyone have any other questions? No more questions, sir. So thank you so much, sir.
Sure.
Thank you so much for delivering a wonderful session and giving us great insights on this topic. Thank you, sir.
Sure. Thank you so much. And thank you for having me. Take care.
Thank you.
వీడియో ఫీడ్బ్యాక్ లింక్ పెట్టాను